and positive C parity, and of course there is also possible higher states, but we are only focused here. So total angular momentum, the lowest one, 0 and 2. So you have pseudoscalar mesons, which have spin 0, which have negative parity and positive C parity, or you have scalar mesons, which have spin 0, positive parity, positive C parity, or 2++, which are tensor mesons. So those are the dominant states which actually do contribute in the physical spectrum to this G minus 2.
Do you have 2 minus plus?
2 minus plus you can have, but I'm not aware there are many states, at least not in the low-lying part of the spectrum. So, and then the higher they are in the spectrum, the more suppressed they are when you calculate loop diagrams. So there is no prominent state, I think. So let me just show you what is known, just a few examples in an experiment. So if you do this fusion of two real photons into hadronic states, for instance, the lowest channels would be pi plus, pi minus, or pi 0, pi 0. So there is a lot of data, mainly from Bell. Bell has measured here these black points quite accurately. So at lower energy, there's no accurate data. So these are all data from Mark II detector, I think it was at Stanford. Here in this range, actually at present, there are new data being taken from BESS. So they will basically extend with the same kind of precision also in this lower energy range, which is actually the dominant range also for the G minus 2. But one sees here a very nice peak. This is just an example. This is just a tensor meson, in this case F2, 1270. That from these cross sections you can extract these 2 photon strengths into these states. And then you can use, so this is basically what goes into particle data book. If you look in the particle data book, 2 photon widths of these mesons, they are coming from these kind of processes. Let's just apply one of these sum rules, which I just explained for you, which is the difference between helicity 2 cross-section minus helicity 0 cross-section as function of energy. But let's, for simplicity, assume that they are completely saturated by meson states which have these definite quantum numbers. So what you see then, so first of all, you can produce mesons with different isospin states, and these sum rules, they are satisfied for each good quantum number. So if you project on isospin 0, for instance, isoscalar states, you should satisfy it. If you project on isovector, you should satisfy it, and so on. If you go to higher flavors in the charm sector, you would also satisfy it. So I will just show you in the time I have one case, namely isospin 0. So what do we know about, let's first look at mesons which have helicity 0. So when you have helicity 0, the dominant states are the ones, of course, which have spin 0. So helicity is a projection of the spin. So you can have, of course, spin 0 projection when you have higher spin, but the dominant one will come from spin 0. So pseudoscalar states are the lightest in the spectrum. So they cannot project on helicity 2, so because you have only a spin 0, so you can only project on helicity 0. So they will only contribute to this side. So if you do this integral, it will always be negative for these states. And eta has been measured, eta is the lowest isoscalar, eta is the lowest isoscalar state, pseudoscalar meson. And so you can calculate this integral, and I just show it here. It is a dimensional quantity, it's a nanobarn when you do this integral. It's a large negative number, okay, minus 190 something, which is just a reflection that only this term contributes. And eta prime, which is the next pseudoscalar meson, has even larger number, minus 300. So these numbers are from particle data book. They directly come from the 2 photon decay width of this meson into 2 photons. Now if you do the scalar mesons, so they're not so well known. So they're scalar mesons at 980 and then at 1370. Also here scalar mesons only contribute to the second term, so also will be negative. They're typically a factor 10 here smaller. This one is still sizable, has a large 2 photon width, like minus 100. So if you add up everything, you will end up somewhere like at 500, minus 500, something, minus 600 here, nanobar. And we know this has to be 0, this is an exact sum rule. So it has to be compensated by meson states which have helicity 2. And indeed, the prominent peak I've shown you before, if you do this, if you use these data and these two photon width and you calculate this, so when you have, this will dominantly contribute to the sigma 2, gives you 450 with a positive sign. And then if you take, Bell actually has measured also higher states, if you take them into account and you do the sum of all these states, you will end up here with minus 89 plus or minus 66. So within the error bars, basically, even with this, with these states, and of course we know there might be higher states which give you small contributions, but it's basically already consistent. So it shows that there is really an interplay. These mesons are not independent of each other, coupling two photons. They have to be highly correlated using such sum rules. In this case, there is a strong interplay between eta, eta prime, and this tensor meson F2. And one can do the same, of course, for isoscalar states, for charmonium states, and so also for charmonium states, it's an interesting case where this works. But I will skip that because I would like to show you some applications for G-2. You find this if you're interested on the slides. So let me just spend 1 second here on, if you go to meson productions where you have virtual photons, so 1 or 2 virtual photons. For instance, let's consider the case first where you have 1 virtual photon, 1 real photon. Then this so-called Landau-Young theorem, which I told you, which says that the coupling of 2 real photons cannot go to a state which has angular momentum 1, does not apply because 1 real photon, 1 virtual photon is not a Bose symmetric, doesn't satisfy Bose symmetry. And then you get large contributions here of axial vector mesons also. So vector mesons are not allowed. So why are vector mesons not allowed? If you have 2 photons, you cannot go into vector meson because what is the parity quantum number of a vector meson or the vector state in general? So it's negative, and if you have 2 of them, so photon is also a vector, so yeah, 2 of them will not go into that, but it can go into an axial vector because axial vector is 1 plus plus, so these quantum numbers would then be allowed. And so there are 2 prominent, or there's 1 prominent, especially F1 state axial vector meson, and I will just show you because I will use it for the G-2, this one. So it has been measured actually. These 2 states have been measured to decay into 2 photons, so 1 real, 1 virtual, at L3, this is at lab. And one can also use another of these sum rules, which I just briefly flashed, I didn't explain it. So it's a combination of other cross-sections. It doesn't matter really here what are the details, I just want to show you that basically they only contribute to one of these terms, and they contribute with 1 sign. If you evaluate the sum rule, and if you look at scalar and tensor mesons, which contribute then to the other, so you see here this is 1 term, so they are 0, and here you have these negative numbers, and the other term, so here they are non-zero, so positive, and here these are basically 0. So you get that this negative number and this positive number, which you get from scalar and tensor mesons, again compensate. So here it works at like 2 sigma level, but it's most likely because not all the states are measured. So you can, particle data book only lists these lowest states. So again, what one sees here that these axial vector mesons are highly correlated to satisfy these sum rules with scalar and tensor mesons. So what it basically tells you, what these exercises show, is it tells you which degrees of freedom will be relevant when you calculate this box diagram, this 2-loop diagram for the G-2. So I would like to spend in the last 20 minutes or so to look at this 4-photon process. So like to scatter light by light and giving rise to light by light. So So from the point of view of a QCD, so it's really a two-loop calculation where you have two scales involved, Q1 squared and Q2 squared. And in general, when both scales are small, we know relatively well how to handle it. You can do effective field theories. If both scales are very large, you can use perturbative QCD. But why this is a hard problem is because you have mixed scales. You have so one virtuality can be small, the other can be large, or vice versa. And usually in these intermediate regions, there's no model-independent tool to describe it ab initio. So you need as much information from experiment possible in order to cover this. And just to give you an idea on so what is basically the physics in this blob, if you do an expansion in large number of colors, so you can actually, or it has been shown, that the leading contributions here correspond to single meson exchanges. So the lightest one, of course, you will have propagators. So the lightest states will dominate. So pseudoscalar mesons will evidently dominate. And then these axial vector mesons, which I just talked about, and tensor mesons. So they will be the dominant degrees of freedom here. If you do in the chiral perturbation theory, if you look at this object here, light by light scattering, the leading contribution, chiral loop contribution, is just coming here from a pion loop, and then you can go to higher kaon loops and so on. So a pion loop will be a dominant contribution. Basically, it's a pi plus pi minus here. And then if you go, when both scales are very large, this blob is just a perturbative quark loop. So, but you have to take all these into account without double counting. So you really need to have a separate calculation for different energy regimes in order to cover this full two-loop integral. So let me focus first on the largest contributions, which actually give rise to the number which I quoted in the beginning, and how to improve on them. These are the so-called single meson contributions, and you can ask yourself, okay, you can calculate diagrams, of course, how do you know this is QCD? So I will show you there is a dispersive approach, and you can, in a dispersive approach, you can show that these single meson contributions correspond to the pole contributions in the dispersion theory. So it's not the full theory, but it's the leading part of this dispersion theory. And the pole contributions here is when you have pseudoscalar mesons. There are three topologies actually of these diagrams. So it's typically it's a two-loop integral, so you have to integrate over these two virtualities. You have 5 propagators, so 3 photon propagators, 2 muon propagators here, and then you have a lepton tensor, which is well known. So this is just here the coupling of 3 photons to a muon, and then everything else is sitting here in a hadron tensor. And this hadronic tensor, it's a 4-point function. So this requires the input of here 2 virtual photons going into this mesonic state, and here a real photon and a virtual photon going into this mesonic state. So these involve these meson transition form factors. So just give you one example of some recent evaluation which we did here. So this axial vector meson, which I showed you is relevant, and the sum rules have shown that this is a relevant state, so have been estimated, and one can just write down the contribution to nu. So this two-dimensional, or the two-loop integral actually can be written, so one can do this in Euclidean space, and one can do it as a two-dimensional integral over the magnitude of the virtuality for one photon and the other, and then you have 2 weighting functions. These 2 weighting functions correspond to the 2 topologies which I've shown you. And these weighting functions, just to give you an idea which regions are relevant to these calculations, are shown here. So these are these weighting functions as function of the virtuality of one photon and the second photon. This is for the first topology. This was, just to come back to this is the first topology. So where you have no cross diagram, and here a non-planar diagram, and the non-planar topology is the so-called second topology. So this is shown here. So what you see is basically this in GeV. So the scales which are relevant are typically when the two virtualities are somewhere in the range up to 1 to maybe 2 GeV. So if one does if one has accurate information in these ranges, you can basically reconstruct this quantity A mu. And okay, this is just here the table of the different contributions which have been calculated. So the largest ones, so this is, we have seen the number, this is now in unit, I forgot to say this here, sorry. This is in units, so all the numbers you see here are in units 10 to the minus 11. So if you remember, the total contribution I've shown you from this light by light in the beginning was 10.5, 10 to the minus 10. So I just showed them here in 10 minus 11, so it should be around 105. So you see the pseudoscalar mesons, they contribute something like 95 or so, the most recent number. I just quote here the numbers which are updated this year. We had a workshop on this in April, where most experts in these fields were there. And what also, the heavier mesons, they were also estimated for the first time in here in some detail with experimental input, and axial vector mesons in particular turned out to be not completely negligible there. So now you can, how to go beyond these pole contributions. So if you, so there's been several new developments to relate this process, so it's basically a two-loop process, to relate this process in using a dispersive framework. So basically it's the coupling of a photon to a spin 1/2 particle, and if you don't know what is happening here, it's just a 3-point function. So at this 3-point function, it's the anomalous, it's the Pauli form factor. So because we are looking at the anomalous magnetic moment. So it's if you have a Dirac particle, so you have a gamma mu coupling, and then you have a sigma mu nu q nu coupling, and this is the G, so the A mu, which is standing in front of this. So this is this, so the Pauli form factor is usually called F2, and it's F2 at virtuality 0. So when the momentum transfer here goes to 0, so this gives you the anomalous magnetic moment. When you write down a dispersion integral of a 2-loop integral, which is of course much more complicated than a 1-loop integral, but it can be done, you have to write down, for instance, let's look at one diagram here, and let's assume that this is a pole propagator, just like a point particle here propagating. You have to write down all possible cuts. So you get here a meson, photon cut, and you get a 3-photon cut. And each of these cuts corresponds to a physical state. So here you would have the process where a photon converts into a pion and a photon. So you have this experimental data. Here you would have a 3-photon state, which is on its mass shell. And if you know these different intermediate state contributions, so the discontinuities from them, from experiments, so you have to relate them to different observables, so both space and time-like. So you're doing this here basically as function of the center of mass energy squared of this photon. So it means it has to be time-like. So this starts, for instance, for the 2 meson cut. So the leading discontinuity here, because the photon is massless, would be the mass squared of this particle. So it starts from m squared all the way to infinity. And the 3-photon cut, because the photon is massless, starts from 0 to infinity. So you need also time-like data here in order to constrain these imaginary parts. Then you calculate this dispersion interval and you reconstruct then the real part A mu. Now, this of course has not been done with data, so this is what several groups are working on this now, but I would like to show you a proof of principle calculation which we did recently, which is already realistic in the sense that it's the contribution which is coming from pseudoscalar mesons. So assuming everything else, so assuming here form factors which are given by single particle poles, so this would be the equivalent of saying that the form factor of pi 0 to 2 photons is given by vector meson dominance by a single pole. So you can do a field theory calculation, and you can do, so a direct to loop calculation is possible in this case, and has been done. And what is shown here is this A mu, as function of the mass of this pole. So in the case of a pion, for instance, this would be 100, this is in GeV, so this would be the pion here, 140. The eta would be here, and then eta prime would be somewhere here. And so this two-loop integral is shown by the black curve. Now, what is shown by the blue and the red curves are the contributions of these two-particle cut and three-particle cut. So basically, this part here, if you reconstruct the two-particle cut from the dispersion integral, you will get the blue curve. If you reconstruct the three-particle cut, you will get the red curve. If you add them, you will get the pink. So the pink is exactly on top of the direct to loop integral, which means, so one has understood all these, so it's quite involved calculations with these phase space integrals. So one reconstructs this correctly. Now, in this case, of course, we have two independent calculations. We have, if these are poles, you can do a direct to loop calculation. That's why you have this possibility. If you have here like a pi plus, pi minus, or another loop entering, you will not be able to do this anymore in a quantum field theory framework in a model independent way. But you can always do the dispersive approach. So you can, it's of course, it will be quite involved, but you can always reconstruct from imaginary parts which you relate to experiment real parts. And so then the hope is that using such calculations one will be able to bring down this error in this line by line. So I would like to come here then to a summary of this part. So I've tried to give you an idea of some new theoretical tools which are being developed for the scattering of light by light into hadrons. And so in particular, some rules are quite powerful because they really allow you, first of all, they're model independent. You can test them in quantum field theory frameworks, and they allow you to really see quantitatively what are the relevant degrees of freedom. And so dispersive frameworks in general for these quantities, such as transition form factors of mesons into two photons, allow to include experimental constraints in this quantity G-2. And so I've shown you a few of these recent evaluations also for heavier meson contributions. So such new dispersion relation frameworks for anomalous magnetic of the muon, of course, if one really wants to push the precision by a factor 2 or more, will require quite close collaboration with experiment, because you need data both for space-like photons, time-like photons, and also decay, meson decays into real photons. And so this will allow them to obtain a more data-driven approach to this hadronic light-by-light scattering. And so the goal here, so this is what I was stating in the beginning, is to obtain a realistic error estimate for this a new quantity. And so basically the outcome of the workshop we had is that the goal should be here to reduce the theory to 10 to the minus 10, which by itself means, so this light by light contribution is roughly 100, 10 to the, 10, sorry, in units 10 to the minus 10. So an error of 2 10 to the minus 10 means you need to know this hadronic light by light with a relative precision of 20%. So that's the goal. So so the hadronic vacuum polarization, you need to know cross sections with a precision of 1%. Here one aims at 20% in order to reach this precision goal. And this will allow them to match the precision of this upcoming new G-2 experiment at Fermilab. And actually what is shown here is the magnet from Brookhaven, which was shipped there with the boat all across the United States, and which just arrived here on the campus here at Fermilab, so which is presently being installed for this new experiment, so which should take data end of 2016 and then into 2017 and so on. Now, in the last 2 minutes or so, I would also like to make like one slide of advertisement. So for those people who are interested and who have not yet made up their mind for their PhD, I would like to mention, but also more generally, if you know people who are interested to do a PhD abroad. So we have an international graduate school in Mainz at the university. In hadron and particle physics, so it's called symmetry breaking. So it's an international PhD program. So we have 12 competitive and attractive PhD positions. Actually, our funding agency is requiring that nearly half of them should be non-Germans. So it's not something. So it's really meant to be an international graduate school, and so lectures are also given in English, evidently. So 2/3 of a postdoc salary, and people have own travel funds. They have there's also a whole lecture program and a workshop program. So people who are interested, they can look at there's a website, you can find this on the slide, and of course you can always contact me. And this is also for exchange programs, so people who like to do we have also a few people who do joint PhD in 2 different countries, so this would also be a possibility. So I would like to thank you very much for your attention.
I have many questions,
yes.
But let me ask 2 first. The first one is that you calculate the single Messin contribution to AMU, and you got the data input for this contribution. But you also mentioned that we can use the language of chiral perturbation theory, and we have a Photon loop contribution. Yes. Can we have the data input for the chiral perturbation theory if I adopt this formula?
Yes, yes. So come back to the data input for the chiral loop, which is basically 2 pion state there, is shown here. So it's here. So the dominant contribution is from pi plus, pi minus. So you can actually see these cross-sections of 2 photons going to pi plus, pi minus are typically like 200 or 300 nanobar at lower energy. This is the threshold region. Pi 0 is way reduced, so it's only like 10 nanobars. So this is by far the dominant. And so as you see, the Bell has very nice data, but unfortunately, so maybe someone from Bell can say, but I think it's really related to the detector. They were not able to go below 800 MeV, center of mass energy of the hadronic state. And because you have the lowest mass states are really dominating in these loop intervals, so if you want to have the chiral loop, you need to have accurate data here. So basically the theory is showing you here there's this big bump, which is basically the coupling of 2 photons into, there's first these Born diagrams, but then also the chiral corrections to that. And they are giving you a big bump here. So in order to really have the data input, you need precise data here. And actually people are, in Mainz, there's a group working, doing these experiments at BESS, and they're analyzing these data right now. So this will be available, I would say, within 1 or 2 years.
Yeah. But then this contribution also contains the pole contribution from F2, right? So
yes.
This belongs to the single Messin contribution. So does it mean that the chiral perturbation theory in fact is more complete? It contains both resonant and non-resonant contributions.
Yes. In order to include the F2 in the chiral perturbation theory, of course, you can say formally you include it to a contact term, right? Now that calculation will not be very accurate. If you include it to a contact term, of course you will never describe the peak. So it can only work if you are at very low energies. If you are far away from that degree of freedom, you can absorb it in a constant. But if you need to integrate over the energy region, if you're just interested in gamma gamma to pi pi at low energy, then you can indeed do that. But in the G-2, you need to integrate over this energy region with a weighting function. So you need to have a realistic description of the spectral function, so to say, over energy. And then chiral perturbation theory only allows you to give a realistic description of the energy dependence in a low energy regime, but not in the whole energy regime.
Yeah, but is that possible to use the extension version of the chiral perturbation theory with just like in chiral perturbation theory with resonance?
Yes, yes. Okay, then people do that. But then you have to go beyond what is pure chiral perturbation theory. That's what people are doing actually. Then of course the question becomes model dependent at some point. It's not, you will not have
yeah, you got a resonance, unfortunately mass is not large enough.